Okay, so we're going to look at exponential functions, and we should be able to do a few things with them. First off, we need to be able to determine if an exponential function is growth or decay. We need to be able to identify the key features. We need to be able to identify the transformations, and we need to be able to graph it. So the good news is the transformations, A, H, and K, are the same as our quadratic and absolute value functions. The problem is an exponential function is going to look different. It's not going to have axis of symmetry or vertex anymore. So we are going to need to learn new key features. So in a graph, exponential growth is when you start small and you increase rapidly. When we look at an equation, we're going to notice that the base is greater than 1. So the number that's being raised to the x power, the exponential part of it, is going to be greater than 1. Because if we think about it, what's happening here is when the power is 0, x is 0, y is 1. Then when 3 is raised to the power of 1, it's 3. When x is 2, it's 9. And when x is 3, it's 27. These numbers are rapidly increasing because we're continually multiplying by 3. As opposed to decay, it's going to start relatively large and decrease quickly. That's because this has a base that's between 0 and 1. We never have negative bases because that would cause an issue with our graphing, but we do have bases between 0 and 1 that cause us to decay. Because from a table standpoint, when we plug in 0, we do get at 1. Anything raised to the 0 power is 1. When we plug in 1, 1/3 to the first is 1/3. 1/3 squared is 1/9, and 1/3 cubed is 1/27. These numbers are rapidly decreasing. So the new key feature that we're going to look at is called an asymptote, a horizontal asymptote. Because this is horizontal, it's always going to be in the format y equals. If you remember, hoi, vux. Before we had axis of symmetries, which were vertical lines. So axis of symmetries were always x equals. Now we have asymptotes, which are horizontal. So they're going to be y equals. And so what an asymptote is basically the tail of the exponential function gets super, super close, but never crosses the asymptote. We can never go below it. So it's basically a do not cross line. So let's look at a graph and see what a growth looks like versus a decay. Now, the problem is that each function is going to have its own parent function. So when the base changes, we get a new parent function. So this is the parent function when b is 2. If the base was 3, we would have a different parent function, but it's the parent function because no transformations have occurred. So I'm going to plug in all of these x values to the function for x. So -2 will go in, then -1, then 0, 1, and then 2. So 2 to the -2 is 1/4 because when we raise something to the negative power, we have to take the reciprocal of it. So it's 1/2 squared, which is 1/4. Then 1/2, then 1, then 2, then 4. We are doubling in size each time. So if we were to graph it, we would have -2 be at 1/4, -1 be at 1/2, 0, 1, 1, 2, 2, 4. And if we were to add in one more, 3, 8, 2 to the third is 8. So you can see this shape is starting really close to the x-axis, getting bigger, bigger, bigger very quickly. So the tail of the graph is to the left and it gets bigger as we go to the right. It increases. And there is an asymptote at y equals 0, meaning there's this do not cross line at y equals 0. We can never dip below 0 because we're going to keep getting smaller and smaller and smaller by a half, 1/8, 1/16, 1/32, but we'll never actually get to 0. So our domain remains all real numbers. Our range is going to change slightly. Because of this asymptote, we're never going to get to 0. So our range is simply greater than 0. Our asymptote is at y equals 0. So because we can't get to y equals 0, this red dotted line, our range is just greater than 0. So these two are always going to be related. And then the new key feature, instead of having a vertex, is just going to be our y-intercept. So we have a y-intercept here of 0, 1. So the decay, we know, is when the base is less than 1, between 0 and 1. So this really should have been to the 1/2 as our base. So our base here is 1/2, which indicates to us that it's decay. So -2, if I raise 1/2 to the -2, that means take the reciprocal. So that's really going to be 2 to the +2, which is 4. And if I fill in the rest of the table, these are the values I get. So you can see this time instead, on the left, I'm going to start higher. And I'm going to decrease as I go to the right. That's what makes this decay. And my tail ends up on the right. So this still has an asymptote of 0. I'm never going to dip below that value. So always all real numbers, it's going to get infinitely wide, but our range is going to stay above 0. We will have an asymptote at y equals 0, and our y-intercept is still at 0, 1. So again, the good thing is that these are the same. These stay the same. So that's good news. A is still going to reflect and stretch and shrink. H is still going to control going left and right. Sorry about that. K is going to control going up and down. The new thing here is that B determines if it's growth or decay. We know it's growth when B is greater than 1. We know it's decay when the base is between 0 and 1. So if the base is 2, write a function that's been reflected and stretched. So reflected and stretched means that A needs to be negative and bigger than 1. So this would be perfect. Again, making sure my base is 2. So it is a growth function, just a growth function that's reflected and stretched. This one wants us to go left. So we're going to do +3 next to x and down 5, which is going to be a -5. And then if we reflect over the x-axis, A needs to be negative. So the number in front is negative. And it's shifted up 6, so we have +6 at the end. So up and down is controlled by the number at the end. Left and right is controlled in the exponent next to x. And the number in front of the base controls stretching and shrinking and reflecting. So if we want something that's shrunk, shifted left, and up 2, shrunk means the number in front needs to be less than 1. So A needs to be less than 1. Left 2 means in the exponent, H needs to be 2. And up 5 means K needs to be +5. So that's this one. A is less than 1. In the exponent, we made it +2 to show it went left. And then outside, we did +5 to show that it went up 5. So our key features are the y-intercept and the asymptote. To find the y-intercept, we're going to plug in 0 for x. So if we do that, we're doing 5 times 2 to the 0 power. 2 to the 0 is 1, times 5 is 5. So our y-intercept is going to be the coordinate 0, 5. If I plug in 0 here, 2 to the 0 is 1, 1 plus 6 is 7, so our y-intercept is going to be 0, 7. The x-coordinate's always going to be 0 because you're plugging that number in for x. The asymptote, which is the horizontal line, only changes when you move it up or down. And if you remember, k is what moves things up and down. So here, k is technically 0. So our asymptote is going to be the horizontal line y equals 0. Here, k is 6. So that means that horizontal line got shifted up 6 units. So now instead of being at y equals 0, it's going to be at y equals 6. So for each of these, let's say what the transformations are, whether it's growth or decay, and find the key features. So I notice the 2 here, so that's a stretch of 2. And I see the -4 in the exponent. That controls going left and right, so this is going right 4. It's growth because the base is 3. So whatever the number inside the parentheses is, that's the growth or decay factor. So it's a growth function. And the y-intercept is going to be at 0, let's see, if I do 2 times 3 to the 0 minus 4 function power, I'm going to probably have to use my calculator to figure out what this is. So a lot of times with exponential, we end up using our calculator. So if I do 2 times 3 to the -4 in my calculator, I get 0.02. That's our y-intercept. And then our asymptote is just y equals 0 because this graph was not shifted up or down. Here, I have a negative in front, so that means it's going to reflect over the x-axis. And the +5 here tells me that this is going to go up 5. Because the base is 1/2, that makes it decay. If I plug in 0 for x, so I get -1/2 to the 0 plus 5, that's going to be 4. Using my calculator, that gives me 4. And my asymptote is going to be at y equals 5. Because I shifted up 5, that's where my asymptote is. And then this last one has an a value of -1/2. So that's a reflect because it's negative, a shrink by 1/2. It's +6, so that meant it went left 6. And it's -1, so that means it went down 1. The base, so the thing that's being raised to the exponent, is 3. So because that's 3, that means that we have growth. If I plug in 0 for x to find the y-intercept, again, I'm going to have to use my calculator. So I'm doing -1/2 times 3 to the 6th power, and then -1. It's a pretty big number, which again, sometimes these numbers are really big or really small because it's exponential. That's my y-intercept. That's what my calculator gave me when I plugged in 0 for x. And then my asymptote is always the k value. So y equals -1. So to graph these, we're going to find the y-intercept by plugging in 0 for x. So if I plug in 0 for x, I get 2 times 3 to the 0, which is going to give me 2 if I check my calculator. So I'm going to go 2 x values above that and 2 x values below that. So now I'm going to do 2 times 3 to the -2 power. That's going to give me 0.22. 2 times 3 to the -1 power in my calculator is giving me 0.67. 2 times 3 to the first is giving me 6. And 2 times 3 to the second is giving me 18. So I want to also plot my asymptote. My asymptote here, because it wasn't shifted up or down, is going to be at y equals 0. So here's my asymptote, and I'm just going to plot these points. The points for these functions are always a little funny just because we're dealing with really big numbers and really small numbers. But I know that it's growth. I always kind of want to know if it's growth or decay as well because my base is bigger than 1. So I'm going to start with my tail here and get really big as the function grows. And notice how my asymptote is denoted with a dotted line. So let's try this last one. I'm going to find my y-intercept by plugging in 0 for x. So I'm doing 1/2 times 0 to the negative 2 plus 1. That's going to give me 5. And then I'm going to go 2 x values above, 2 x values below. And I'm just using my calculator. So I have negative 2 minus 2 plus 1. That's giving me 17. I have 1/2 to the negative 1 minus 2 plus 1. That's giving me 9. Then I'm plugging in 1. That's giving me 3. And then I'm plugging in 2. And that's giving me 2. My asymptote, because k is 1, I have an asymptote at y equals 1. And I know my base is giving me decay. So I'm going to have an asymptote at y equals 1. So I'm going to draw my dotted line there. And then I'm just going to plot the points that do fit. Not every point from our table will always fit. So I'm just plotting the ones that do fit. And because it's decay, it's going to start big. Oops. And get small with my tail on this side. That's always the decay shape. Start big and get small.